Hello, my name is Francisco Campos. I'm the Director of Operations at ENGYS. My presentation today is about Elements, our CFD software tool for vehicle design. More specifically about the new features and enhancements coming to version 3.4.0 this November 2021. Before I move into the main topics of my presentation, I would like to introduce my company ENGYS. We are global providers of CFD products and services. We started the company in the UK in the year 2009, and we've been operating continuously ever since. Our main focus as a company is to exploit open source technologies in order to provide CFD software tools for enterprise. And there is a historical reason for that. It's because we have had a very long association to form an open forum since 1999. So we take advantage of this knowledge and all the know-how that we have accumulated over the years in order to produce high quality CFD software tools with a focus on open source technologies. We have over 200 plus active customers around the world. Some of these customers are buying our products and using our products. Others are coming to us for services such as consultancy or custom developments. And we service these customers from 8 offices worldwide, 4 of which are in Europe, 1 in the United States, in Australia, in South Africa, and in Brazil. And in those places where we don't have a local presence, we rely on a very well-established network of resellers, which cover Asia and other places in Europe and as well as in the Americas. In terms of our enterprise CFD products and how our vision as a company reflects on the quality of such products, we combine the benefits of commercial CFD software tools in the shape of an easy-to-use graphical user interface, best-in-class technical support, and extensive written documentation, with the inherent advantages that open source CFD technologies have to offer in terms of full capacity of code customization and the free scalability that we can get through open source by removing the restrictions that licenses and HPC licenses impose coming from other traditional CFD software tools in the market. The result is a very compelling set of CFD software tools in the shape of Helix, our general purpose CFD software tool, and Elements, which is an extension of Helix specially designed for vehicle design applications. And in addition of the default capabilities that Helix and Elements have to offer, we also provide a series of add-ons to extend such default capabilities. In particular, Elements Adjoint, which is a continuous adjoint solver for topology and shape optimization, and Elements Couple, which is a set of block couple solvers for incompressible and compressible applications. The origins of our CFD software tool Elements goes back to 2012 with the creation of a joint venture company called Streamline Solutions between ENGYS and the Auto Research Center, or ARC. ARC are based in Indianapolis, United States, and they're well known for the automotive engineering expertise and their wind tunnel facilities. And we've combined this expertise with the well-proven know-how of ENGYS in computational fluid dynamics and software development to create elements for CFD automotive analysis using open source methods. Talking about elements in more detail, it's important to mention all the different applications that we can cover with elements today. And you can see in this slide that we can cover pretty much every single aspect of CFD simulation in the context of vehicle design, starting with external aerodynamics in the shape of virtual wind tunnels, thermal management, HVAC and cabin comfort, acoustics analysis and noise prediction, soiling, motorsports applications, and then finally, automatic design optimization using Adjoint. So what's new in Elements 3.4.0? Well, Elements 3.4.0 is a major release, which means that all the new features and enhancements that we have introduced in this new version cover pretty much all the main components that make up our software. And these include mesh, setup, the solvers, visualization, and add-ons. And of course, because all the main components are reflected in the graphical user interface, if you're already using Elements, then you will be able to access pretty much most of those new features and enhancements in the GUI for your own benefit. Starting with the new features in Mesh, we have improved the snapping algorithm in order to be able to capture difficult feature edges like the ones that we see in acute or reflex angles, like in this example here. So we in this particular case, we have to grow a mesh into a very, very narrow space without actually perturbing or destroying the quality of the feature edge that gets captured there. And we can do so by implicitly calculating the snapping by a plane-to-plane line intersection, which actually happens automatically. This is, of course, ideal for things like bladed components, turbomachinery, contact patches, and so on. Another thing we have improved in mesh is we have introduced a new splitting option to generate near wall layers around sharp trailing edges. So this is a very simple example here where we have a splitting off, and then we switch on splitting at the rear of a wing profile. So at the trailing edge of the wing profile, we have more control now over what happens at the trailing edge, and we can increase the quality of the mesh in these regions to avoid generation of negative pyramid volumes. So it's ideal for low Y+ grids. We've also improved mesh optimization in 3.4.0. We've added additional quality check controls for mesh optimization when using our strut algorithm. If you remember, there are 3 meshing algorithms in our software, and the strut algorithm is the preferred algorithm when trying to generate low Y+ grids, where we need additional controls in the near wall region. We've improved accuracy of mesh optimization during the snapping stage, and you can see this in the example on the right, where we compare the mesh or the low Y+ mesh creation around a bladed component in version 3.2 in comparison to version 3.4.0. And you can see that in the tip region, we can achieve a much better result with 3.4.0 than before. And then finally, we have also done work to reduce the turnaround times for mesh optimization. So there is an additional benefit in terms of speed up when meshing during the layer addition. The last thing to mention about mesh is that we have introduced a new set of tools in the graphical user interface to measure quality metrics. You can see in the example here our new histogram widget, where we can display quality metrics like non-orthogonality, skewness, and so on in the shape of a histogram. And this histogram is fully interactive. So you can click on the bar and on each one of those bars and then display in the show in the display the elements that fall within that range. And of course, this is very useful if, for example, you import mesh from a third-party tool and you want to verify that the quality of that grid is compatible with the kind of quality that our solvers accept. Moving now to setup and the work that we have done in this particular set of components in 3.4.0, I'd like to start with the so-called generalized internal boundaries, or GIBs. And this is something we have been presenting over the last 2 years or so. And what it enables us to do is to apply standard boundary conditions on internal faces of the mesh. And of course, those internal faces can be moving. So we have added support for multiple moving GIBs in one model, so we can prescribe rigid body motions and complex rigid body motions at different stages inside the same model, as we can see in this example of an internal combustion engine where we use 3 GIBs at the same time, one representing the intake valve, another one representing the exhaust valve, and another one representing the moving cylinder or the head of the cylinder going up and down. And in addition to this, we've also added support for thermal solutions in the context of GIB. So we can also solve for temperature while using generalized internal boundaries in our simulation. Regarding new boundary conditions in 3.4.0, there are 2 things to mention. The first one is the new inlet synthetic turbulence generator based on the ATSM method. Which we can use to apply specific levels of turbulence at inlets. And you can see that in this simple example where we apply turbulence at the inlet, and we can see how that turbulence obviously develops from there. This is particularly useful if you are looking at atmospheric boundary flows, or if you want to prescribe a certain level of turbulence inside a wind tunnel, just so to match real life, what you actually measure in experiments. The second thing is the new time varying point data boundary condition for inlets. And we use this when to map data collected from experiments into the CFD models. If we want to use experimental data and apply that experimental data in a transient fashion as an inlet in the CFD model, we can use this boundary condition. We had this functionality in the past. We used to use standard libraries available publicly in OpenFOAM, but as you can see, under certain circumstances, the mapping wasn't working particularly well. So we have moved now to a new triangulation method, and you can see that the results are very good in comparison to what we had before. In terms of turbulence models, we have been very active in this front over the last 2-3 years since we started working very closely with quite a lot of Formula One teams here in the UK. As a matter of fact, we work with more than half the teams in the paddock this year. And through this collaboration, in many cases, with the Formula One teams, we have introduced several turbulence models, including these two turbulence models that I have to mention here. The first one is the KKL omega transition turbulence model. So we've done quite a lot of work just looking at different transition turbulence models, very important in certain aspects of aerodynamics. And then the other one is the Mentor's K omega SST model with curvature correction, which has become very, very popular, especially if you are looking at things like rotating flow or string-wide vortices. So in this example, looking at a wind profile and looking at the vortex that generates on the tips of those things, K omega SST with curvature correction, shows the right levels or predicts the right levels of vorticity in these kind of examples. Finally, in terms of physical models, two things to mention. First one, the additions that we've done in terms of thermal human comfort. We've done quite a lot of work in this particular area to service the customers we have in the building industry mainly, even though it also applies to other sectors like automotive, for example, or transportation, so looking at comfort inside trains, for example, or planes. And we've added an option to calculate the so-called WVGT index, which is calculated based on the standard ISO 7243 in this case. And the other thing we've done is expanded the capabilities we have already to calculate comfort indices following the ISO 7730. This is the same standard of PMB and PPD. Predicted mean vote and predicted percentage dissatisfaction, which are very well-known comfort indices in generally. And what we can do now is to calculate an index called drop rate using the CFD turbulence intensity instead of prescribing a user value. So we can calculate this cell by cell using the actual CFD turbulence intensity from the solution. And the other thing we've done is to expand the capabilities of our conjugate heat transfer solvers in order to accept passive scalars as well. So now we can solve for passive scalars when doing CHT in case we want to release a tracer or simulate something like a smoke, some kind of passive scalar.
Regarding the changes and additions to the Aerodynamics Wizard in Elements 3.4.0, also known as the Virtual Wind Tunnel Wizard. The first thing to mention is the extension to the wheel treatment and how we actually model wheels and how we set up wheels and wheels models in the graphical user interface. So we've extended the generalized reference frame-based wheel treatment in our tool to include two new approaches. One is what we call the GRF surface approach, which is patch-based and is fully automatic using our swept-based method to identify all the regions in the tires and the wheels that are actually rotating, including tire frets where that's present. And then the other one is what we call the GRF volume approach, which is a manual approach to enable the user through the graphical user interface to identify the volumes for the tire frets and other wheel components. So he has complete control over how to generate a GRF volume where the rotating source will then be applied to approximate the rotation of the wheel. Another change that we have introduced in the Aero Wizard in 3.4.0 is related to the ride height tool. And we fully refactored this tool in this new version to add new labels and tooltips for a more intuitive interface. And also, we've also added a new ruler widget to the tool in order to simplify the setup and make it more clear to the user. So we can see in this example here that now we have the ruler tool. We can actually measure distances and changes to the ride height in order to adjust the attitude of the vehicle in the wind tunnel prior to the simulation. Lastly, it's worth mentioning the new options that we've added to the configuration files in the Aero Wizard in 3.4.0. The configuration files control what is available to the users in the graphical user interface when it comes to defining an external aerodynamic simulation. The first thing that we've done is to add the ability to record geometry transformations as part of these configurations files, so the user has the ability of automating things like translations, rotations, or scales when importing geometry into the Aero Wizard tool. The second one is that we've added support for elements couple solvers to the configuration file. So where before it was only possible to define best practices using segregated solvers, runs, or DES, now it is also possible to create best practices and automate processes using block couple solvers if the user has access to the elements couple add-on. The third thing is the inclusion of support for what we call bi-axle configurations for wheels. And what this means is that the user now has more control over the models that are used to approximate the rotation of the wheels on an axis by axis basis. And then finally, we've added support for side wind inside the configuration files in order to enable users to simulate yaw analysis. So if they want to do yaw studies, it is possible to automate this process as part of the Aero Wizard and to embed the best practices for those yaw analysis processes using the specific new configuration options that we've added. Moving now to the new features we've introduced under Solver in 3.4.0, most of the work that we have performed in this area over the last year or so have been focused on what we call the Unified Solver Framework, or USF. USF is a new framework we've created to bring together all the solver features into one single application in order to simplify the developments and also make it simpler to maintain as we go forward. In this version, we have extended the USF to include support for subsonic single-phase compressible flow solutions, in addition to the already existing support we had in the past for conjugate heat transfer solvers. We have also introduced support for the compressible flow solutions in the USF framework inside the graphical user interface. So it's possible to convert all cases to the new format, the new USF format, by changing the preferences under File Preferences Unified Solver Framework, as you can see here.
Further to the work that we perform as part of the expansion of the Unified Solver Framework to support compressible flows, we also look at the buoyant terms in the equations. And there is a very good reason for this. If you look at this particular example here of a heated wall at 1300 Kelvin inside a room where the sides are open boundaries and the room is at 300 Kelvin, when we compare the solution of this problem with a well-known commercial tool to the solutions that we achieve using the standard libraries in OpenFOAM for this particular kind of problems, you can very easily see that the solutions are quite different. We are comparing velocity magnitude in this case. And the reason for this is because the standard formulation of OpenFOAM exhibits severe instabilities in explanation areas, which of course lead to a lack of convergence.
In order to overcome these issues, we propose a new formulation of the pressure equations written in terms of gauge pressure rather than the standard formulation in OpenFOAM, which is based on what we call the PRGH, which is no other thing than the pressure minus the static head. And we have also changed the formulation of the buoyancy source in the equations from cells base to phase base. The result of this is that we no longer need to tweak the reference height to improve stability, and also the use of gauge pressure improve the floating point accuracy of the solution as well. Now, when we compare the results from the commercial CFD tool with the results achieved in our software, we can see that the velocities in this particular case compare very, very well. And all the instabilities that we experienced before with PRGH have been removed from the solution.
In addition to the changes that we applied to the buoyant formulation, which I explained in the previous slides, we've also added some changes to the total pressure boundary conditions in order to increase even further the stability of buoyant flows and natural convection flows. And this change is mainly focused on the addition of this new switch called added static head to the total pressure boundary to account correctly for surrounding static head pressure profile in open boundaries. And you can see this very clearly in this example where we have a source of heat and a rising plume typical of a buoyant flow. And if you notice the results on the open boundary where the total pressure is applied, you can see a much more stable solution when we add the static head switch as opposed to the solution using the standard total pressure boundary without correction.
Moving to the next set of components in the graphical user interface, we find the View tab. And the next couple of slides summarize the changes that we have introduced in 3.4.0 to improve the 3D display and the visualization in the GUI. The first one is related to what we call the local GPU rendering. And this is used when we connect to a remote server using the client provided in the graphical user interface. What we can see in the example here is that with the new improvements that we have introduced in local GPU rendering, what we can do is take the visualization data from the remote server and bring it locally to the client server in order to use the local graphics card to render the display. And you can see in this comparison here that the results in 3.4.0 can be displayed much faster and much more smoothly in the new version than it was done previously in 3.3.2 and before. The second feature we've added under View in 3.4.0 is the ability to export 3D objects from our software to third-party rendering software tools such as Blender, Maya, 3ds Max, and so on. You can do this using 3D file formats such as X3D, PLY, and BT to take the CFD results from our software and bring them to the third-party software tools for generation of photorealistic renders and complex animations. With regards to the add-on modules in Elements 3.4.0, I would like to start by mentioning a couple of new features in Elements Adjoint. The first one is related to the symmetry of sensitivities. What we've done is to add the ability of defining a plane around which the sensitivities are forced to be symmetric. By extension, of course, the optimal shell will also be more symmetric. This is ideal if you are trying to optimize a design which itself has geometric symmetry, as it is the example of this manifold. The second feature relates to the improvement in convergence speeds for sensitivities when doing topology optimization. And what you will notice if you are already already using Elements Adjoint is that the speed of convergence of the optimal shape is much faster in this new version than it was in previous releases of our software. With regards to the Elements couple around module, the new features we've introduced in this component in Elements 3.4.0 are very much related to Elements Adjoint. We have created a new adjoint block couple solver, which enables us to calculate sensitivities around 100 to 300 times faster than using the traditional segregated approach. And you can see that in this plot here, where we look at the convergence speeds for sensitivities to minimum drag, while comparing the segregated solver to the block couple solver. And you can see that the convergence trends are very similar, but the number of iterations that are required for using the block couple solver are about 100 times faster than the number of iterations that are required when using the segregated approach. The implications of this are huge because we can calculate sensitivities almost instantaneously and add those sensitivities as part of the standard solution without having to pay an additional price in terms of turnaround times. And just to finalize, I'd like to mention a few miscellaneous developments that we have introduced in 3.4.0. The first one of these is quite important, and it relates to the way we build Helix Core, which is our open source simulation engine. So we've replaced the traditional WMake compiler with the CMAKE compiler in order to take full advantage of all the features that CMAKE has to offer. So if you're already using our software and you compile Helix Core in your own system, hopefully you will find CMAKE much simpler and much more feature-rich than WMake. The second is related to the implementation of additional tooltips in the GUI. So if you move the mouse pointer over a specific component in the GUI, you will see a tooltip that will show you and explain what that component is for. So hopefully it will help you understand what all the different things in the GUI are used and how they can be used. And then finally, we've introduced a new search bar for the object tree to filter items in the GUI. And this is particularly useful if you are managing a very large case with loads and loads of parts. You can use these wildcards and enter them in the bar to just hide everything else and just facilitate the way you work in the graphical user interface. And that brings me to my closing remarks. The new version of Elements 3.4.0 will be released in early November 2021. It is very much in line with the release of Helix 3.4.0, which also happened around the same time. There are over 100 new features and extensions in 3.4.0 with respect to 3.3.2. So there's an awful lot of work that is gone into this version and that happened over the last year or so. We have very ambitious long-term development goals, and this will lead to our next major release of 4.0.0 in either 2022 or beginning of 2023. There's a lot of emphasis on extended vehicle design simulation capabilities, and a lot of that comes from the feedback that we receive from you, from our users, that obviously shape our development strategy. So we will always try to listen to what our customers want and what our customers need in order to drive our developments and drive the quality of our products. Thank you very much for your attention. Don't miss the ENGYS user group meeting in 2022. You can register at that address. Thank you.